So here we will look at some of the different kind of steel which are studied from the point of their metallurgy. So steel can be broadly classified into two categories. One is plain carbon steel, another is alloy steel. So within plain carbon steel we have four subcategories based on the amount of carbon content present inside. First is low carbon steel, mild steel, medium carbon steel and high carbon steel. Most of the times low carbon steel and mild steel are often clubbed together, but still we will have a look at the differences which can possibly occur. And in the alloy steel we have among many different varieties, we look at three major varieties here. One is HSLA, that is high strength low alloy steel, that is another is maraging steel, and then is stainless steel. So if you look at plain carbon steel, let's start with the low carbon steel. So the steels which have a carbon content less than 0.1% are usually classified as low carbon steel. And if you look at the stress strain curve from the mechanical behavior point of view for the low carbon steel, we see that in the stress strain curve for the low carbon steel we have Luder band formation observed. So that is in fact in a sense the formation of various bands in the material at different locations, and they propagate to extend the deformation throughout the material, and this deformation is generally called yield point elongation, and occurs there is a sudden drop in the yield point, and at this point there is a large elongation for at a constant stress, and this terms as the yield point elongation. And this is usually not desirable in the steel because it leaves marks on the surface, and that is also known as orange peel effect, and that is one of the disadvantage of using low carbon steel. Although low carbon content always promotes good weldability, we'll see in mild steel. So to overcome this particular operation, there is another kind of steel which also contains less than 0.1% carbon and which does not show orange peel effect, that is called the dual phase steel. So this particular steel, the material is heated in the austenite region and then quenched, and it contains only 20 to 25% martensite and along with that ferrite, and this particular microstructure gives us good formality and is got very high strain hardening, and also ductility does not decrease. So this is a very useful rope from the point of view of automobile application, in which we want to have a lightweight material and save on the fuel cost. Apart from that, low carbon steel also suffer from strain aging effect, in which if the material is released from the stress is released after a certain point, and then again without giving certain time it is again stressed in the same level, we see that its yield point increases, and at the same time this yield point phenomena vanishes. So one of the reasons for this is yield point phenomena occurs basically due to pinning of the solute atmosphere by the solute atoms like carbon and nitrogen present. So they pin the dislocations and they do not allow dislocations to move. So this leads to formation of Luder band formation. So when when the material undergoes strain, so the dislocations are freed from the atmosphere of solute atoms, and they are able to freely move, and that's how we get the new strain stress curve. Second is the mild steel, which is very most widely used steel among all the categories in the applications such as angles, channels, and all the structural applications. One of the most biggest advantage of this steel is that it has very good weldability. So in the steels, when they undergo welding, so there is a heat affected zone which forms, and that zone typically means that it is a zone which cools down much more rapidly than the surrounding material, because of the first the air cooling, and second is the presence of cold in contact with the cold surrounding matter. So because of that there is a probability of formation of martensite, which may weaker the material, make it brittle, but due to the presence of very low carbon contents, the HZ, the martensite formation in the HZ region is avoided, and there is no further treatment necessary to give in the mild steel in the welding. So all the structural application where it is not possible to take the material ex situ and give them any treatment in the as it is as condition, so it is most widely used. Another is the medium carbon steel. Medium carbon steels most commonly found application is in the rail steel. All the rail structures are mostly made from medium carbon steels. They have, apart from carbon, small amount of manganese addition, which shifts the eutectoid transformation further towards the right, and we have almost pyrrolitic structure, although it's just 0.5% carbon. And one of the varieties of this is Hadfield steel. If there is high wear resistance, that contains more than 12% manganese and has got very high wear resistance. Similar to this is in the high carbon steel we have spring steel. So as the name suggests, spring steel, we need to have one of the most important property, that is resilience, that is the ability of the material to return to its original position in the elastic regime. So the energy absorbed during this region, higher the energy absorbed in the elastic regime, higher the resilience of the material. So it is defined, or basically in terms of properties we can say yield strength versus modulus ratio. So higher is the yield strength and lower is the modulus, higher is the resilience. Modulus being the property of the material, we cannot, it's a structure insensitive property, we cannot play around with it, but so it is desirable to have very high yield strength material if it is to be used as spring steel. So most of the time it is used in quenched and tempered condition, and the alloying elements such as manganese and vanadium are added. Manganese obviously leads to increase in hardenability, and vanadium also refines the grain size. So these are some of the broad four categories of materials in the plain carbon steel. In terms of alloy steel, we see that high strength low alloy steel are very commonly used and most popular. So they, as we can see, because of the low carbon content, they possess good weldability, and apart from that they have so one of the reasons why they are called, they achieve high strength in spite of the low carbon content is the presence of alloying elements such as niobium and vanadium. So they strengthen the steel by the two mechanisms. One is they refine the grain size. So precipitates of so both of these elements have very strong carbide formation tendencies. So niobium carbide collects at the grain boundaries and pins down the grain boundaries of austenite in the austenitic region and does not allow the grains to grow. And at the same time precipitates such as vanadium carbide, they are dispersed around the matrix in the ferrite region during transformation of austenite to ferrite and lead to precipitation hardening and by the mechanism of impeding the motion of dislocation. So they, at the same time of good weldability, they can also be used in the places which require higher strength than the low carbon steel. Another is the maraging steel. As the name suggests, maraging comprises of two terms, that is martensite plus aging. So till now we have used martensitic steels, or like we have used martensite for high strength. So in this particular maraging steel we have a high amount of nickel addition, that is 18% nickel. So that obviously gives first hand impression that this increases the cost of this particular steel, but and it has a very low carbon, 0.03% carbon, so formation of martensite is very difficult. But if this is quenched, we form martensite which is very soft, that is not brittle at all. But if this is aged at certain temperature, we get precipitates of Ni3Al because nickel plus titanium aluminum is also added. So this gives us very finely dispersed precipitates, and they give very high strength to this particular steel. See, this is used only in specific applications where very high strength is required. Next is stainless steel. Before we see stainless steel, we should first look at the two types of elements which can be divided, which can be added to steel as alloys, and what are their role. So if you look at the phase diagram of the iron carbon phase diagram, we see that the alloying elements play two kinds of role. One is one are classified as ferrite stabilizers, so they increase the ferrite or the delta phase field and decrease the austenite phase field, gamma phase field, and they also lead to formation of gamma loop. Another austenite stabilizers, they increase or expand the gamma phase field, and in certain circumstances it is also possible that gamma phase field extends to room temperature and there is no ferrite formation. So ferrite stabilizers, if they have no austenite phase field, so they cannot be heat treated because there is no austenite phase transformation possible. So so based on this, they are stainless steel. Obviously they are stainless because they have a passive oxide layer of elements such as chromium oxide, which prevents them from degradation. So they are classified into 3 categories based on their properties. One is austenitic stainless steel. So austenitic stainless steel are basically, as the name suggests, they are added, they have addition of alloying elements which are austenite stabilizer. Main is nickel. So one popular grade is 18-8, that is 18% chromium, 8% nickel. It has totally austenitic phase field, and they have good formability because austenite FC structure, they have good formability at room temperature, so they can be cold worked. And another is the ferritic stainless steel. Ferritic stainless steel have chromium or another equivalent of ferrite stabilizer, and but one of the reasons is that they have very low formability, so they are used less commonly than austenitic stainless steels. Although austenite in stainless, and another category is martensitic stainless steels. So in the ferritic stainless steels we have very less portion of carbon, so the austenitic phase field is almost eliminated, but if the carbon content is increased without addition of austenite stabilizer, there is we still get austenitic field, and upon quenching from the austenite we have martensite formation, and they have much higher strength than the ferritic stainless steel, so they are used in application where hardness is a desirable property, such as knives and cutlery and other sharp edge materials. So so these are the broad categories of steels available, although there are much more detailed varieties of steel being developed continuously through the industrial process, but these are the starting point from where we can do these metals.